Hello YouTube, this is Eric from Coder Snacks. Today we're doing another live video, this time with a Google interview question. Write a function that determines if you can win a game where you have a line of pots of gold, and each turn you can choose a pot on either end, and your opponent does the same, and you win if you get more gold than your opponent when there are no pots left. We'll do this one using a plain text editor. I want to note, this video is long. I've said before you should generally practice with an IDE and tools and save whiteboard style practice for closer to your interviews, and this is why. It takes far longer this way, and you can't get instant feedback about your code. Keep this in mind as you structure your practice. As you watch this video, pretend that you're the interviewer. As I'm writing the code, watch for mistakes, things that you would comment on, and make a judgment about the code and what you want me to improve on as a candidate. Use this to improve your own skills. Let's get started.
Good afternoon, YouTube. So this time I'm not trying this at 5 in the morning. We'll see if I can do this with a little more energy than last time. And we have a problem that we found on Glassdoor again. This one was under the Google section, and it says you have pots of gold arranged in a line. I've kind of modified this a little bit. Each containing some coins. Each turn you can pick a pot on either end of the line. Then an opponent will pick a pot, repeat until there's no pots left, and determine whether or not you can get more coins than your opponent. So the first thing I would do here is ask for an example. They would probably provide me with one, but let's come up with something. So for example, you might have a list of pots like this, and I can choose either the 60 or the 10, and then my opponent picks whatever's left. So let's say that I pick the 60, then I would have 60 coins, and my opponent could pick the 10 or the 10, and they would have 10 coins, and then I would pick the 90, and they would pick the 10, and we would win. And so in that case, we would be able to win. Let's try to think of a case where we can't win. So something like, if we have just something like this, then we can only pick one of the 10s, and then they'll pick the 90, and we'll pick the other 10, and we'll lose. So that's the sort of thing that we might do. Now, the first thing that comes to mind when trying to solve this is, can I solve this in a greedy way? Like, so should I always take the side that has the most? And I think that that's not going to be the case here. One, because it would be too easy. That's a bit of meta thinking you might not want to engage in an actual interview, but I'm also thinking that there might be some case in which you pick one side and then your opponent can pick something ridiculous, like let's say it's 10, 10, 160, and you might pick the 60 and then your opponent can pick the 100. I don't know that this exact one is going to work out, but something like that. So before we get into coding and so forth, so first we want this to be kind of like a Google interview. So let's give ourselves a timer. Let's say 35 minutes. The reason I picked 35 minutes here is because interviews at places like Google and Facebook and Microsoft tend to be in the 45, 50, 60 minute range. But you usually don't get the entire time to do coding, right? There's usually a few minutes at the beginning or at the end, or both, where you're, answering some kind of questions about what kind of projects have you worked on in the past, or where do you want to be in 5 years? Hopefully not that kind of question. But then at the end, you usually have a few minutes to ask them questions. So it takes 5 to 10 minutes off the interview. So we're going to start with 35 minutes. So we have 35 minutes up there. What kinds of questions would I ask the interviewer? What am I optimizing for? Time, space. This one I think is going to be pretty clearly time optimization. But what else? How large is the list going to be? How many coins could be in each of the pots? Do I have to worry about things like overflow, for example? If I solve this in Python, it's not a big deal, but can pots have 0 or negative coins? Those seem like some good questions. That's about where I would start. So let's assume that all coins contain non-negative numbers of, all pots contain non-negative numbers of coins. Let's say that we're optimizing for time. let's just start there. So I do want to find, before we really start, a case where greedy doesn't work, so that when we have our own solution, we are pretty assured that we have a solution that works. So I think something like this is going to be right. So let's work through this one in our heads. So if we pick the 60, then the opponent picks the 100, and we each get 10 more, so it's 70 to 110. If we pick the 10, then our opponent either picks the 10 or the 60. If they pick the 60, then we get the 100. If they pick the 10, we get the 100. So it's better to pick the 10 than the 60. So this is a good case, and we should be able to win this. So how are we going to solve it? Recursion seems natural, right? Like if we have some function that's like take a list of numbers and determine whether or not we win or lose, then what we should be able to do is this is a little tricky because we have an opponent in play, but it should be either like we take the first element of the list and see whether the opponent loses or wins, but we have to keep track of the amount of gold that is in here. So maybe we say like the current score is 0. I'm not in love with this approach, but I think it will work out. Let's see how it goes. So in this case, for example, we would take the first item and we'd have a score of 10. Well, actually, we're going to probably have to say minus 10, because the recursive call is going to be on the side of the opponent, right? Because it's going to be the opponent's turn next. So we might say that either we'll do one of these sorts of things where it's we're going to take one item off of either end of the list. So len of list -1. Something like this. We're going to write actual code in a moment. I'm not going to worry about the off by 1 case. So we would have something like this, and then we would return whether if both of them are win, then we cannot win. We return lose. But if either of them are lose, then we return a win. So let's try to code something like this up and see how it works. So what we're going to do is we're going to have a function that is can pot of gold winning, say. And we'll take the list of pots and we'll take the current score. And this will return true or false. So, okay, good. And what we're going to do is we're going to say return, well, okay, so I'm not going to try to make it fancy and do some sort of one-liner with this to start with. So we'll say first result equals pot of winning, pot of gold. And actually, I'm going to take off this winning wins. Okay. So first result equals pot of gold wins. And we're going to take, as if we took the first pot, so pots 1 from 1 on, and the score will be negative pots 0 plus score. Do I think that that's right? I don't really. So, but we'll come, well, okay, so this is being passed the score with regards to us. So it's the score plus the pot. So let's, and I believe that this is correct, but we'll test it at the end. So then we want last result. So the result then, if we take the last pot, and it'll be pot of gold's win, and that will be pots up to, not including the last element. So this is going to be something I'm going to make a flashcard for later, I think. Normally, it's not inclusive, so length of pots minus 1. Because if we're length of pots, it would be the whole list, and minus 1 means we're taking the last one off. And then, so that'll be pots minus 1 plus score. And I don't have enough room, so we'll put it over here. This is, I would, you know what? We're not using whiteboard. I would normally just kind of scribble it in the side. Let's make this a little bit smaller. No, I want you all to be able to see it. So we'll just leave it like this. Okay, good. So then we want to say, and I'm just getting something that works first, and then we'll try to improve it. So so what we're saying is it returns true if when. So if first result and last result return false, because first result and last result is as the opponent sees it. So either way, the opponent wins. So we cannot win. Else return true. And this is clearly not optimal. Anytime you have something that's like, if Boolean return false or if Boolean return Boolean, you should fix that. So how do we make something that is the same there? Then we're going to say, okay, return not first result and last result. Okay. That seems really simplistic, but let's see if it works. So we start with our function saying 10, 10, 100, and 60. Okay. And with a score of 0. And this recurses into two possibilities. Either 10, 100, 60, and right now we have it with a score of 10, which I think is incorrect. We want that to be a score of negative 10 because it's looking at it from the opponent's side. So we're going to change this to negative the whole thing. And we'll see how that works. And then the same thing here. All right, so this is now negative 10 and f of 10, 10, 100 with a score of negative 60. Okay, let's look at each of those. So this will return, so guess what? We need a base case. Should always write your base case first. Didn't do that. So here, if length of pots is 0, but we remember from last time, if not pots, then return. So from this point of view, if it's my turn and there are no pots left and there's a positive score, then we win. So return score is greater than equal to 0. Now this is a great question that we should have asked the interviewer. What happens in the case that's a draw? So we've said here, determine whether or not you can get more coins than your opponent. That might make this a little difficult, in fact. Because if it's a draw, then it's kind of like both sides lost. And we kind of aren't dealing with that the way that we want. So is that going to change what we return or how we want this function to work? For now, because the problem is if the opponent thinks, well, I have a draw so I lose, then us winning is going to propagate up. So that, I think that's going to make it so that I want to return the score instead of the Boolean. So let's do that. So we're going to return the score given optimal play. And I had better do this way. Okay. So if not pots, return score. And then this should return. So with first result and last result, we want the better of the two of them. So we want to return max, and so max first result, last result, and then we're going to need some sort of auxiliary function that's going to call this and return whether or not score is greater than 0 or not. So let's leave that like that right now. All right, so now we're back to this. So here you can either take the 10 and so this is takes the 10, or you can take the 60, in which case we're left with this. So now what this should be when it takes the 10, it should be 0, because we had minus 10 points going into this, and we took a 10, so it's 0. And it's reversed, right? So let's look at it. Let's see what we got. Pot's 0 in this case is 10, and the score is minus 10, so we got 0. That's right. Now for this one, it should be minus 50, because we had minus 10, we took the 60, so we have 50, but when we recurse, we're returning it as if it's the opponent's score. So here we have negative pots minus 1, which is the 60. 60 plus negative 10 is 50, and that's what we wanted. Or negative that. So, sorry. Negative 10 plus 60 is 50, and then minus that. So this is doing what we wanted. Okay, good. And I'm going to, just for the sake of kind of my own time, I'm going to just finish like one half of this out and make sure that it works, because you don't want to have a test case that's too large, right? So let's finish just one of these and see if it kind of works the way that we expect. So here we have a score of negative 50. We can either take the 10 or we can take the 100, and if we take the 10, then the score should come back as, or sorry, if we take the 100, the score should come out as negative 50, and this should, because our negative 50 plus 100 is 50 reversed, right? Otherwise, we take the 10, in which case it comes back as 40. In this case, either way, we get, so minus 50 plus 10 is minus 40, and this is empty with 40. This is empty with minus 6, or no, minus 140. This returns false. This returns true. So this one returns, it's actually returning two trues and two falses, right? So, and then in this case, that means that, oh no, we're returning the scores now. Whoops. So, yeah, okay. So here we're returning 40. Here we're returning minus 140. And so the best case here is a score of 40. So let's see if we think that's true. And we do think that that's true. What we should do in this case, we should take the 100, the opponent will take the 10, and we'll have 40 points. As opposed to the case where we take the 10 and they take the 100, which leaves us minus 140. Okay, so I'm pretty convinced that this works. And then what we'll do up here is we'll do an auxiliary function where we say def pot of gold with the pots, and we will return pot of gold wins, although that's a very misleading name now. Let's call it score, and let's fix the other places where we call it here. And this is getting all messed up. So let's now put, let's do what we probably should have done in the first place and just put it on its own line. Whoops. Not as good as it could have been. I am very used to Vim, although I don't do this very well in Vim either, to be honest. So anyway, that's what that should be. This is score, return pot of gold score for the pots, and 0 is greater than 0. Okay, so I believe at this point that this works. So what is the runtime complexity of this thing? Well, we have n pots, and for each decision, or for each pot, we have 2 decisions. We can take, the left or the right. And there is definitely some overlap here, but this function doesn't deal with any of that. So this function is probably O of 2 to the n, because we have n choices, and each choice we have 2 choices for, right? So we have n pots. Each time we remove 1 pot, we have 2 ways of doing that, 2 to the n. So how can we improve this? When we have recursion, we should always think about dynamic programming, and we should always think about memoization. So how could, in a programming situation, I would tend to go towards memoization first, because it's usually easier than the dynamic programming aspect. So let's look at this and see. And usually, if you do it right, they come out to the same sort of runtime, right? Because the size of the dynamic programming table is basically going to be the size of the memoization table. So what would I memoize here? Well, it's easy to memoize on pots and score, right? But that's not actually what we're going to want to do, because the score is going to vary very much depending on which branch we take, and I think honestly we should not be passing the score around everywhere. I think that that's a mistake. Like, what we should be doing is we should be saying, okay, at each branch the result is I take this many points plus the number of points, or minus the number of points the opponent could get for the rest. So let's actually fix that first. So if we just say pots, right, and we say if not pots, return 0 now. And the first result is basically whatever I would get for pots 0 plus, or minus, because it's basically whatever the opponent is going to get for the rest, right? Pot of gold score for the rest. And then here it should be pots minus 1, not whatever I just put, minus the rest. We're going to actually use our mouse here. All right, good. and then we still return the max. Now, just very quickly, do we think that that works? So if I have some list of pots and it's 10, 10, well, 10 and 60. Let's just do a very quick thing because I'm pretty sure that this works. So what should happen is that the first result is going to be 10 plus f of, 10 minus f of 60, or 60 minus f of 10. This f of 60 will be 60. It'll be 60 minus 0, right? Because there's nothing left. So it'll be 60, which will give us the minus 50 that we expect. So I'm pretty confident that that works. Okay, so that's a better recursion, and that would allow us to memoize on pots. But we'd rather not memoize on, say, some sort of subset of the list. We know if we have some list of pots like this, right, then we only care about parts in the middle. Like, we can't have something that's like A, C, E, F, right? Because you can't have taken from the middle, right? It has to be some like subset of, it has to be, we have to have taken from one end or the other, right? So what we should be able to do is we should be able to take the pots and memoize on like a start index and end index sort of thing, right? So if instead up here, and this actually was broken like this, so we should do this. So I'm going to copy this and try to modify it. I'm copying it so that later when we try to review this, we can see whether this code actually works at all. So here we want to memoize on the 0 and length of pots minus 1. And we could have passed those as optional parameters, but I chose not to. So here, start and end. So this recursion finishes. So we need a cache. And here we're going to global the cache. Now, I would probably, in an interview setting, ask the interviewer whether they wanted me to go for the recursive, or not the recursive, the dynamic programming solution or the memoization solution. And if given the choice, I would go for the memoization solution. But many interviewers will see that as a little bit lesser than a pure dynamic programming solution. So I would ask and then go towards the one that they want. But since I don't have an interviewer to ask, I'm going to do the memoization solution and see how far we can get. So we're going to global the cache. And so what is the base case now? The base case is start equals end. There are no more pots to look at, and we're saying that here that the number isn't inclusive, right? So if we have some list like 1, 2, 3, or let's make it a little easier for us to talk about 0, 1, 2, right? This is going to get passed with pot of gold score, the pots, and 0 and 2. And so what happens is, well, so that's actually wrong then, right? Because if we take the 2 off, then we take the 1 off, this will be 0 and 0. So what we need is that start is greater than end, and this will return 0. If we had it be inclusive, then, or if we had it be exclusive, then that would have been correct. But now it's like this. So, okay. Good. So if the start is greater than the end, then return 0. If start end in cache return cache of, start end. Great. And then we're going to want to do the same thing that we were doing before, except that here what we're saying is the start has moved forward 1, or the end has moved forward 1, or moved back 1. And then before we return, we need to cache the result. So this will be cache of start and end equals max first result, last result, and return that. So let's make sure that we think this is kind of working. We bring the cache in. The cache is a dictionary of the key is start end, and the value is the amount of gold you can win, right? If start is this is wrong. If start is greater than end, then return 0 instead of not start is greater than end. Let's make double sure of that. Start is 0, end is 2. We should not be returning anything, so 0 is not greater than 2. Okay, great. If start end in cache, then we return that. Otherwise, we actually calculate the result. And then we put it into the cache, and then we return the result. This is a little inefficient because why are we doing this max thing twice? But it's really not a big deal, and it would probably be worse to pull it out of the cache, or immeasurably better. It's not a big deal. It's a little worse code-wise. Well, let's fix it because it's a little worse code-wise. The reason it's a little worse code-wise is because we don't want to have this kind of duplication. What if later I have to change the code and I forget to change it in one of the places? So we'll say instead result equals max first result, last result. And then we'll change both of those. So the cache is equal to the result and return the result. Okay, so we have 6 minutes left. Let's see if we can get to the dynamic programming solution. So what does this actually look like? Let's take our 10-10-60 thing from above, right? So here we go. I'm making tables, and this is 10. Oh, I'm so good at drawing on this. 10, 10, 60, 100. You know what? I'm probably going to edit this part out and just try to do it over here. So edit, edit, edit. Sorry. All right. So we have 10, 10, 60, 100. I probably won't edit it out. So you all will get to laugh at me. It'll be good. So the idea is going to be that... Oh, no, this isn't quite right. What we want is we want to be able to say for some subset of the list, right? Like we want to have start on one axis and end on the other. That's not quite right. What is the dynamic programming solution for this going to look like? That's interesting because normally you would like to pull the result out like at some point here, but that's not what's going to end up happening. All right, well, what does our table... so a good thing if you're trying to go for the dynamic programming solution and you have a memoization solution, what does our cache look like right now, right? So we had a list that was 10, 10, 160, and we have a start on one side and we have an end on the other, and the end is 3, 2, 3, 2, 1, 0, and the start is 0, 1, 2, 3, and you start like, so what are the end results? The end results are, well, let's just actually do this 0, 1, 2, 3. So, except even that's not quite right, because we need another, I'm gonna call it null for now, not none. Thank you. So if there are no, right, so if there are no pots either way, right, then the result is 0. And if it's from 0 to 0, the result is 10. If it's from 1 to 1, the result is 10. If it's from 2 to 2, the result is 100. And if it's 3 to 3, the result is 60. And now, what? So the problem I'm having here is that, unlike most dynamic programming I've seen in the past, there's this kind of negative thing going on. And it's difficult to know kind of what to do with that. So, okay, what should happen? So, each of these cells should be the value of, if you were the first player, what is the end score if you have some sublist left? This null thing doesn't actually work out, I don't think. So let's leave that. So, okay. If I have a list that is from 0 to 1, and I'm the current player, I get 10, my opponent gets 10, so that should be 0. If it's 10, 10, 100, I get 100, my opponent gets 10, I get 10, so this should be 100. So what I'm doing here is I'm saying, okay, I don't know what the relationship should be in this dynamic programming table. I'm going to myself calculate it and see if I can see a relation. So, and we know that, like, we should be moving so we have 1, 1, right? It should have something to do with, so how do we get to 1, 1, right? We either had to be at 0, 1 or 1, 2. And it's going to have something to do with those two cells, right? So if we have the whole list, then we know that I win by taking the 10. My opponent takes the 60, right? So minus 50, 50, and 40. So this should be 40. And then we're not gonna finish this, but let's see how far we can get in 40 seconds. So this cell can't happen. Well, I mean, it's 0, right? And all of these are 0. All of the lower quadrant. So now we're left with this one. So if we have 1 to 2, the answer is 90, right? Because it's the sublist is 10 to 100, 10 and 100. I take the 100, they take the 10. Okay. With the sublist 1 through 3, I take, regardless, they're going to take the 100. So I take the 60. Up, time's up. Okay. So I feel like we were getting pretty far in the dynamic programming solution, but we needed a few more minutes. So I'm going to stop the interview here, and we'll talk about it more during the wrap-up. So see you guys then.
So, how did I do? Let's take a look at the code and my performance. Pause the video here if you want to make some final notes. There are always things to improve on, But while we strive for perfection, we don't need to reach it to be successful. What's important is improving and finding effective ways to make ourselves better. In my opinion, this is a medium-level problem for Google, Facebook, Amazon, and so forth. As an interviewer, I think this problem is challenging, but it is straightforward in being a pure recursion to memoization DP style of problem. The best problems are ones that have a variety of possible solutions to weigh and discuss. I took the whole 35 minutes to do this problem, and while it might have been slightly faster with an interviewer, I still think this problem would have taken the whole time slot. It's reasonable for someone to take 35 to 40 minutes on this problem. If you can solve it faster than this, you're in great shape. Before we look at code, let's discuss some general interview tips. This interview was better than last time in terms of energy and verbal tics, but there were still quite a few.
So before we get into coding and so forth, so first, it should be either like, because,
An interviewer is not going to be dinging you for these things, but it is something to work on. It will make you sound more professional and skillful. One good thing to emulate from this video is not seeming stuck. Especially at the end when the dynamic programming solution was not coming, there was always progress. Always be doing something. Writing code, explaining your thoughts and next steps, and so on. Always be working towards a solution. Another good part was flexibility about changing code. We'll discuss this more in a moment. Let's talk about some specific pieces of the interview, and then we'll discuss the final code. This line of code was strange. Why use negative indexing in one place and length in another? I did this because I didn't remember how negative indices worked in slices, and I wanted to avoid an off by one error, but I only made it look strange. It would have been better to say what I wanted and how I would have researched it if not at a whiteboard. This would give a better insight into my thought process. Especially in the pressure of interviews, everyone forgets some things, but an interviewer looking at the code as it is may assume I don't know I can use negative indices in slices. I'm making a far bigger deal out of this line than I would in a normal interview, just to make a point. It's okay to admit you don't know something. It's better to show that you're self-reflective and won't hide problems. We all make mistakes. Next, let's talk about testing. It's a good idea to simulate your code by hand after you've written a whiteboard solution, as you'll often find bugs the way we did. However, it's also a good idea to start with smaller, even trivial cases. Had I done so, I would have shaken out some of the bugs much faster. Finally, before we dig into the code itself, one thing to remember. Regardless of your skill level or how you feel the interview is going, have confidence in yourself and your code. Making negative remarks about your abilities in your code doesn't gain you any points.
We try to review this, we can see whether this code actually works at all.
There's a difference between that and being humble but confident. Strive for the latter. Be harsh on your code but kind to yourself. Let's talk code. Here is the initial recursive code now in my editor with a few additional tests added. When we run it, we get this error. I mistyped the function name. After we fix that, the recursive code works fine. This code is pretty solid, but as an interviewer, what's more interesting is the path that led here. Being flexible about changing your code is important. This code changed several times before reaching its final state, and it's a common problem to get attached to a piece of code and not want to get rid of it. Even worse is getting attached and making multiple ineffective patches to try to fix it. If there's something wrong with the code, don't fear change, fix it. Sometimes this is difficult. It feels bad to change code. It feels wasteful somehow, as if the effort we put into writing the code is wasted if we discard it. Instead, recognize we couldn't have written the better code without the things we learned by writing the earlier code. Let the old code go. It played its part. We saw a bit of that hesitation here. There's duplication that I hesitated to get rid of with the justification it's not much better. Just fix it. One thing that bothers me about this recursive code is the auxiliary function. A common anti-pattern I see is thinking you need to have an auxiliary function to do recursion, but usually it's not necessary. Here, what we wanted to return, the win and loss, was different than what we chose to recurse on. In this case, I think it's the cleanest, but generally don't do this. Let's move on to the memoization code where we had a few more errors. Before we look at the completed code though, there's one thing I want to call out from the process. Without knowing anything about the surrounding code, this is wrong. If I wanted this, start less than or equal to end is better. Additionally, this code is ambiguous. Not has a lower priority than the comparison, but if you don't know that, this code is unclear. Moving on, here's the final memoized code with the same test from before. There are 3 bugs. The first one is the same as the first time, the misnamed function calls. Did you find the other 2 during the interview? If not, I'll pause a moment so you can look. Look at the code for first result and last result. The recursive calls use the new indices, but I still get the first and last pots in the list. We should use the start and end pots instead. Here's the new code. The third bug is in the cache. In this code, we create a global cache and use it to look up previously computed results. But the cache uses start-end indices, not a list of pots. When we call the function, we need to flush the cache, which we don't. We could reset the cache in the pot of gold method, but we should not use a global cache anyway. We can pass a cache to our pot of gold score function. The cleaner version of the code looks like this. So the memoized version basically works with a few bugs. Finally, let's discuss the dynamic programming solution, which I didn't finish during the interview. How can we approach it? In our memoization solution, we're recursing using the start and end indices. Let's begin with a table of all the possible start and end indices. What values do we know? We know all the values where start is equal to end. It's the value of the pot itself. Let's put those in. We also know everything where start is greater than end, and those are 0. What cell are we looking for? The one where start is 0 and end is maximum. Now, how do we fill a particular cell? If we look at our memoization solution, we can find the answer. We're either taking the start pot or the end pot and then subtracting the corresponding next state, which is our opponent's score. For example, let's go back to the table. What answers do we need to calculate the final state in yellow, start equals 0 and end equals 3? Either we take the start pot 0 and subtract the state for start equals 1 and end equals 3, or we take the end pot and subtract the state for start equals 0 and end equals 2. To calculate a cell, we'll need the cell to the left and the cell below. We'll work diagonally, running through the table in stripes like this orange stripe, using the answers we have to get the answers in the current stripe. When the table is full, we'll get our answer. For example, the first cell in orange here is the sublist start equals 0 and equals 1. Either we take the start pot worth 10 and subtract the answer for start equals 1 end equals 1 and get 10 minus 10 equals 0, or we take the end pot worth 10 and get 10 minus 10 equals 0 the other way. That one's kind of boring. Let's do another. Here, we either take the start pot worth 10 and subtract our opponent's answer worth 100 below, or we take the pot worth 100 and subtract our opponent's answer of 10. The max of these two, negative 90 and 90, is 90, which is our answer for this cell. We continue this way until the table is filled. Here's code for the dynamic programming solution. If we have no pots, return false, since 0 coins is not a win. We make our table and then populate the main diagonal with the values of the pots. Then we iterate diagonally, filling the table, and return our answer at the end. In general, how did I perform? In my opinion, again, this was reasonable. I got to an O of n squared solution using memoization with a few minor errors. It wasn't great, it would have been better to get the dynamic programming solution, and there were a few places where I made strange-looking coding mistakes. Hopefully, you can learn from them. Some interviewers find the memoization answer to be a good result, and some prefer to see the DP answer, making this result a bit of a toss-up. However, give yourself a little slack when working without your IDE. We have these tools for a reason, and you will make some mistakes without them. Just do your best to improve. What's your opinion of my performance? Let me know in a comment. Next time, we're going to work on a solver for a popular word game, Boggle. Given a grid representing a Boggle board, return a list of words you can form. If you're not familiar with the rules for Boggle, I'll put a link in the description. I hope you got something out of this video. If you have any questions, comments, something I've missed, or problems you want answered or covered, let me know in the comment section below. And if you enjoyed this video and want to see more, it would be great if you liked the video, subscribed, or both. I really appreciate it. See you here next time on Coder Snacks.